Hello friends. I am Viddya Patil, Assistant Professor in Department of Mechanical Engineering in Sharad Institute of Technology, Polytechnic Yadra. Today we are going to continue our problem series 5.3 for the unit Refrigeration and Air Conditioning for the subject Power Engineering and Refrigeration. Today in this session we are going to cover the problems related to vapor compression system in the refrigeration and air conditioning. Okay, first we take problem. I read the problem statement first. A simple saturation cycle using R12 is designed for taking a load of 10 tons, and the vapor is in dry saturated condition at the beginning of the compressor, and the evaporator temperature is equal to 268 degree Kelvin, and the condenser temperature is equal to 308 degree Kelvin. We have to find the mass flow rate, power required in kilowatt, and coefficient of performance. And here they are given the values of H1, H2 and HF3 is equal to HF4 values are given, that are the enthalpies values which are taken from pH diagram. That is H1 is equal to 185 kilojoule per kg, H2 is equal to 206 kilojoule per kg, and HF3 is equal to H4 is equal to 70 kilojoule per kg. Okay, first we understand this process. Okay, here in vapor compression cycle, the TPH and TS diagrams we have to draw here. Okay, and for that purpose here they are used the process, that is compression, condenser, expansion, evaporation. These processes are carried out here in this vapor compression cycle. We understand first these cycles. In compression cycle, the low pressure vapor in a dry state is drawn from the evaporator during the suction stroke of compressor, and during compression the pressure and temperature increases until the vapor temperature is greater than the temperature of the condenser cooling medium. Okay, in compression. Next is a condensation. Okay, and here in figure 2 to 3 we see here condensation process. In condensation, when high pressure refrigerant vapors enter the condenser, which is come from the compressor, cooling medium absorbs the heat and converts this vapor into liquid, that is converts vapor into liquid in condensing processor. Next is 3 to 4, that is expansion. Okay, in expansion, after condensation, liquid refrigerant is stored in liquid reservoir, and the liquid from the reservoir is passed to the evaporator through the expansion valve. So the expansion valve reduces the pressure by keeping enthalpy constant, and so the process taking place in throttling process. Next is the vaporization, that is evaporation process. In evaporation, this low pressure liquid refrigerant after expansion enters in evaporator, where the condensable amount of heat is absorbed by it, and it converts into again liquid to vapor. So this vapor at low pressure is sucked in suction line of compressor, and this cycle runs. Okay, this is all compression, condensation, expansion and evaporation process. Okay, so what happen when dry saturated vapor at point 1 enters into compressor? The compression process is isentropic, okay, which increases the pressure from evaporator pressure to condenser pressure, and at point 2, that is superheated vapor enters into the condenser, where heat is rejected. Okay, in evaporation process heat is absorbed, but in condensation process heat is rejected. That's why in condensation process vapor to liquid conversion is carried out, but in evaporation again liquid to vaporization process is carried out. So heat is rejected at constant pressure, in condensation. So due to the rejection of heat, temperature of superheated vapor is reduced to saturation temperature, and there where removal of heat result in condensation and vapor converts into liquid at point 3. So at point 3, that is throttling of liquid take place, and which reduces the pressure by keeping enthalpy constant. Here we can see there is a constant enthalpy. So due to the reduction and gets converted to saturated vapor, which can enter in suction line of compressor. Okay, here we can see there is H3 is equal to H4. That's why here enthalpy is constant. So again, here in this problem we have to calculate the mass flow rate and power required and coefficient of performance. For that purpose, first we calculate they are given the load, that is 10 tons. Okay, capacity is given 10 tons. So we convert this in kilowatt by tons into kilowatt by multiplying 3.517, that is refrigeration effect. 1 ton of refrigeration effect is equal to 3.517. So they are given 10 tons, so 10 into 3.517, so 35.17 kilowatt load. Next is the enthalpy. Here they are given in problem enthalpy H1 is equal to 185 kilojoule per kg, HF3 is equal to H4 is equal to 70 kilojoule per kg. So to calculate the refrigerating power required, first we have to calculate refrigerating effect. So refrigerating effect is equal to M, that is mass of refrigerant effect, mass of refrigerant into H1 minus H2. So here we H1, so here refrigerating effect, that is here H1 minus H4. So refrigerating effect, that is 35.17, and we have to calculate mass flow rate, we so keep as it is, and H1 is 185 and H4 is 70. So mass flow rate of refrigerant is equal to 0.3058, so 3058 kilojoule per kg. Next we have to calculate the compressor power. Okay, we have to calculate power required in kilowatt. So for that purpose we have to calculate compressor power, and to calculate compressor power we use formula, that is mass flow rate, that is of refrigerant, M refrigerant into H2 minus H1. Why we take here H2 minus H1? Because at H2 there is a compressor outlet and at H1 there is a compressor inlet, and we have to calculate compressor power to run the compressor. That's why we take here H2 minus H1. So mass flow rate we just calculate 0.3058, and H2 is equal to 206 minus H1 is equal to 185. So compressor power is equal to 6.422 kilojoule per kg. Next we have to calculate coefficient of performance. We know the formula for the coefficient of performance, that is refrigeration effect divided by compressor power. Then refrigeration effect is equal to 35.17, and compressor power we just calculated 6.422. So COP for the refrigerator is equal to 5.47. Okay. Now we see next problem. A VCR working on R134A operates between saturation temperature minus 2 degree centigrade and 34 degree centigrade. Refrigerant is saturated at the entry of compressor and assumes no subcooling. So enthalpy of refrigerant at the end of compression is 444 kilojoule per kg. Find COP of the system. Find also power required per ton of refrigeration capacity. Use following data for R134A. refrigerant. Here temperatures are given for -2 and 34 degrees centigrade. The values of enthalpy in kilojoule per kg at liquid state and vapor state are given. So at liquid state 197.33, vapor state 397.51, and for 34 degrees centigrade enthalpy at liquid 247.47 kilojoule per kg and at vapor state 416.85 kilojoule per kg. Okay, now we see in vapor compression system. Okay, in last problem we see in vapor compression system the processes, that is compression, condenser, expansion, evaporation. These are all processes we see, but here there is one another process is added here, that is superheating. Okay, so superheating, that is when a simple vapor compression cycles, the compression suction is dry saturated vapor. But if some liquid refrigerants enters the suction line of compressor, due to the wet compression, lubricating oil present in compression will be washed off, the causing more wear and tear of compressor, and effective line of this compressor reduces. So the compressor is the main vapor coming out of evaporator is allowed to stay for some more time in evaporator to ensure dry saturated or superheated vapor at evaporator exit, thus increasing the temperature of refrigerant vapor more than the saturation temperature in evaporator, that is known as superheating. Okay, so effect of this superheating is the suction temperature of compressor increases and increasing the compressor power, but it also increases the refrigerating effect. Therefore COP of system remains more or less constant. So the superheating is not done to increase the refrigeration effect or COP, but it is done to increase the life of compressor. That's why superheating is necessary. Here in this problem we can see here they at point 1 dash to 1 there is a superheating, that is before the compression. Okay, and in TS diagram also we can see superheated by 15 degrees centigrade they are given. So here in this problem we have to calculate the power required per ton of refrigeration capacity. That's why first we note down the various things which are given in this problem, that is enthalpy at the end of compression, that is H2 is equal to 444 kilojoule per kg, they are given in that problem. But enthalpy at compressor inlet, okay, so compressor inlet, that is H1. Okay, at a compressor inlet that time the refrigerant is in vapor state. That's why they are given given in this table the temperature value at compressor at -2 degrees centigrade at the entry of that compressor, that is in vapor state. That's why we can take here the value of H1 enthalpy as a 397.51, that is vapor value we can take here. Next is the enthalpy at the end of condensation, that is H3, because H3 is the end of condensation. End of compression is H2, but end of 2 dash is the entry of this condensation, but end of compression is H3, and we here in this they are H3, that is in end of compression condensation. The vapor is heat is rejected in condensation process. That's why the liquid vapor phase is converted into liquid phase of that refrigerant. That's why we can take H3 for the liquid phase. Okay, at 34 degrees centigrade, because when refrigerant enters from goes from the compressor, that's time their temperature increases to the -2 to 34 degrees centigrade. That's why at a liquid stage, for 34 degrees centigrade, at the end of condensation, that is H3 is equal to 247.47 kilojoule per kg. Now we can consider here the process 3 to 4, that is throttling procedure. That's why enthalpy before the throttling is equal to enthalpy after the throttling. That's why H3 is equal to H4. That is H3 is 247.47. That's why H4 is equal to 247.47 kilojoule per kg. Now COP for the refrigerator we have to calculate. Here the values of enthalpies are given. That's why we use the enthalpies formula for the COP refrigerator, that is H1 minus H4 divided by H2 minus H1. So putting the values of H1, H2 and H4, we calculate the value of COP refrigerator as a 3.23. Now we have to calculate refrigerating effect, and for the 1 ton of refrigeration effect is 3.517 kilowatt. So to calculate the compressor power, we again use the formula for the COP refrigerator is equal to refrigerator effect divided by compressor power. So refrigerating effect for the 1 ton of refrigeration, that is 3.517 divided by we have to calculate compressor power, and COP refrigerator is 3.23. So compressor power is equal to 1.088 kilowatt. Okay. Next problem statement is that R12 refrigerating machine working on vapor compression cycle that receives saturated vapor at 5 degrees centigrade at the entry to compressor. It is compressed isentropically. So refrigerant is condensed at 40 degrees centigrade. We have to determine coefficient of performance, power per ton of refrigeration, theoretical piston displacement per ton of refrigeration, and use the following properties of refrigerant, that is enthalpy of refrigerant at compressor inlet, that is H1, that is 189.7 kilojoule per kg. Specific volume of refrigerant at compressor inlet, that is 0.049 meter cube per kg. Enthalpy of refrigerant at compressor exit, that is H2, 203.2 kilojoule per kg, and enthalpy of refrigerant at condenser exit, that is 74.6 kilojoule per kg. Condenser exit enthalpy, that is H3. And here the representation of pH and TS diagrams are we have to draw here. That is we know that we already discussed about the pH and TS diagrams. Okay, now we have to calculate the we have to calculate here the COP, power per ton of refrigeration, and theoretical piston displacement per ton of refrigeration. So for that purpose, first we have to calculate the we have to note down the properties of refrigerant, that is H1 is equal to 189.7 kilojoule per kg, H2 is equal to 203.2 kilojoule per kg, H3 is equal to 74.6 kilojoule per kg. And we consider for the throttling process, that is enthalpy before throttling is equal to enthalpy after throttling. That's why H3 is equal to H4, that is 74.6 kilojoule per kg. Now we have to calculate the COP of refrigerant, that is H1 minus H4 divided by H2 minus H1. So by putting the values of H1, H2 and H4, we get COP for the refrigerant, that is 8.525. So refrigerating effect is equal to 1 ton. That's why 3.517 kilowatt. So refrigerating effect is given refrigerating effect is equal to mass flow rate m into h1 minus h4. So RE is for 1 ton 3.517. We have to calculate m. So h1, putting values of h1 and h4, we can calculate m is equal to 0.030556 kg per second. Okay, so we have to calculate power required per ton of refrigeration. So power required per ton of refrigeration, that is m h2 minus h1. Okay, power required to drive the compressor, that is per ton of refrigeration. That's why here take compressor work h2 minus h1. Okay, so by putting the values, we got power required per ton of refrigeration is equal to 0.412 kilowatt. Now they are asked to calculate theoretical piston displacement, okay, per ton of refrigeration. So mass flow rate into specific volume of refrigerant at compressor inlet. So mass flow rate, mass m we calculate just now, that is 0.030556 kg per second into specific volume of refrigerant, they are given 0.049. So theoretical piston displacement per ton of refrigeration is equal to 0.001497 meter cube per second. Okay, by dividing 60, we converted this seconds into minute by 0.0898 meter cube per minute. We converted in second into minutes. Now we see next problem. R12 refrigeration system works on vapor compression cycle and the refrigerant is subcooled by 5 degrees centigrade. Before entering expansion device, show the cycle on pH and TS chart. Calculate COP, power required to drive compressor for 1 ton of refrigeration capacity. R12 has following properties: enthalpy at compressor inlet 137, that is H1 kilojoule per kg. Enthalpy at compressor discharge H2 142 kilojoule per kg. Enthalpy of saturated liquid at exit of condenser, that is H3 is equal to 110 kilojoule per kg, and specific heat of liquid refrigerant is 1.12 kilojoule per kg Kelvin. So here the processes is given, and here there is a subcooling is given. Here the why subcooling is done here, we in last problem we see the process of superheating, okay, and here the subcooling is given. Okay, the process of subcooling refrigerant below the condensing temperature for given pressure, that is known as subcooling or undercooling. Okay, the effect of this subcooling is, due to the subcooling the refrigerating effect increases, or for same refrigerating effect the circulation rate of refrigerant decreases, and therefore the COP of the system increases. That's why the subcooling is desirable and is done to increase the refrigerating effect and coefficient of performance of the system. And this process of subcooling or undercooling is shown in this figure also, that is in 3-3, that is after condensation there is a subcooling takes place, and in TS diagram also you can see after condensation to expansion there 3-3, that is subcooling at 5 degrees centigrade. Okay, now we have to calculate from the properties of refrigerant. We note down H1, H2 and H3 three values, and enthalpy of refrigerant at inlet to expansion device H3 is equal to H3 minus Cp T3 dash minus T3. Okay, and T3 dash value is 1110 and 1.12 into 5. So we can calculate here the enthalpy of refrigerant at inlet to expansion device, that is 104.4 kilojoule per kg. Okay, now we consider the process 3 to 4 a throttling process, and again from that enthalpy before throttling is equal to enthalpy after throttling. So H3 is equal to H4 is equal to 104. Okay, so COP of the refrigerant is equal to H1 minus H4 divided by H2 minus H1. So putting the values of H1, H2 and H4, we can get COP of refrigerant, that is 6.52. Now the refrigeration capacity is one for the 1 ton. That's why refrigeration effect is equal to 3.517 kilowatt. So refrigerating effect is also given mass flow rate of refrigerant m into H1 minus H4. So refrigerant effect is for 1 ton, that's why 3.517, and by putting the values of H1 and H4 we can get the value of m, that is 0.10788 kg per second. So power required to per ton of refrigeration, that is m H2 minus H1. H2 is the end of enthalpy at the end of compression, H1 is the entry of compression. That's why power required to drive the compressor, that's why power required for the ton of refrigeration m H2 minus H1. So putting the values of m, H1 and H2, we can get power required per ton of refrigeration is equal to 0.5394 kilowatt. Okay, in this session we cover the problems related to vapor compression cycle and related to superheating and subcooling also. Thank you. Next session we cover the next problems related to refrigeration and air conditioning systems. Thank you.